Hi, I'm Sayantika Bhowal, postdoctoral fellow at ETH Zurich, working with Professor Nicholas Spalding, and welcome to the video abstract of my talk on the detection of hidden magnetoelectric multipoles and their case-based analogs using Compton scattering that I will be presenting in the upcoming QMAT conference. Quantum materials are known for their exotic properties that emerge due to the coupling between various fundamental degrees of freedom of an electron. Often these degrees of freedom entangle to form composites. One of such examples is magnetoelectric multipole, which plays a crucial role in the magnetoelectric response of a material that describes the generation of polarization due to an applied magnetic field and vice versa. Physically, magnetoelectric multipoles represent an asymmetric magnetization density in absence of both inversion and time reversal symmetries. The antisymmetric magnetization density represented by this magnetoelectric multipole can be decomposed into three irreducible components. The first component is the magnetoelectric monopole, represented here by a blob of magnetization density with the magnetization vectors pointed in the outward direction. The second component is the toroidal moment, represented by a head-to-tail kind of spin arrangement. Finally, a 5-component magnetoelectric quadrupole moment, and one of its component is shown here. To understand the magnetization density represented by each of these irreducible components are indeed important to the magnetoelectric response, let us take the example of magnetoelectric monopole, where all the spins are pointed in the outward direction, so as a result, there is no net magnetization. Now, due to the canted spin, there is also local electric dipole moment, and these local dipoles are arranged in such a way that the net polarization is also zero. Now, if we apply a magnetic field, the spins tend to cant towards the direction of the magnetic field, and as a result, a net polarization is developed in the direction antiparallel to the applied field. Therefore, we can see that a magnetoelectric monopole can give rise to a diagonal magnetoelectric response. Similarly, it can be shown that a toroidal moment can give rise to an off-diagonal magnetoelectric response, and so on. Since these multipoles are important to understand the magnetoelectric response, a natural question is how to detect them. The detection of these multipoles are, however, not so straightforward, simply because they neither have any net polarization nor any net magnetization, as we just saw in the example of magnetoelectric monopole. Therefore, we need to design experiment to detect them. And this is exactly the motivation of our work. So in the talk that I will be presenting in QMAT conference, I will discuss about the detection of the magnetoelectric multipoles using Compton scattering. The idea here is based on the duality between real space and momentum space. Due to this duality, the antisymmetric magnetization density of a magnetoelectric multipole transforms into an antisymmetric electron density in the reciprocal space. As a result, we can probe them using Compton scattering. Here, the measured quantity is Compton profile that carries this information of electron density in the reciprocal space. Since we have an antisymmetric electron density, therefore, we expect an antisymmetric signal in the Compton profile. In my talk, taking the example of lithium nickel phosphate, I will discuss about the factors, the parameters that control the strength of this signal. An exactly opposite situation exists for a non-magnetic system with broken inversion symmetry. Here we have an electric dipole in the real space that transforms into an antisymmetric magnetization density of a magnetoelectric multipole in the momentum space, resulting in an antisymmetric magnetic Compton profile. Therefore, we can see that using a non-magnetic probe, such as Compton scattering, we can detect a magnetic object, that is, in this case, magnetoelectric multipole, whereas a non-magnetic system can also give rise to a magnetic Compton profile. To hear more about magnetoelectric multipole, please attend my oral presentation on the very first day of QMAT conference, and thank you for listening.